All right, thank you for making this special time because of the scheduling conflict. So when this class was scheduled, I wasn't told about the time and I didn't realize the conflict with the seminars I'm organizing from 12 to 1. So today is a seminar and next Monday will be another one. So for these 2 days, I will try to move this class time, but try to record it in case you cannot make it. So today we're meeting at 2. And I think for next Monday, I will send another announcement before next Monday, we will meet at 10. We'll meet 10 a.m. here. So in the same room, and I'll try to record it. So don't worry if you can not make it. And because I think for recording, the quality would be better if I use the projector and paper instead of the board. So right for the special times, we'll record the lectures just for information. That's the announcement. And I expect to assign you the first homework this Wednesday after the Wednesday class, and it'll be due in 2 weeks. Okay, so that's an announcement. And this is actually a class I was teaching this morning in the same room for the bioinformatics PhD program. But this method we discussed has some relevance to this class, to this linear model class. So that's why I think it might be good for me to briefly talk about this just as a, how to say that, as an application, as a related topic for you to think about. And specifically, this is a very brief high-level description of this method on a website where many people follow for method choices. But just look at the description here together, and I want to hear your thoughts about whether your current background allows you to understand it, or maybe we can revisit this again after we talk about generalized linear models. So basically, in the first step, a negative binomial generalized linear model is used to fit each gene with observed. Okay, you can ignore this jargon, but with the covariate. In the second step, each model parameter, including the intercept, slope, and negative binomial dispersion parameters, is regularized based on the relationship between parameter values and gene mean. So the mean is just the mean of the outcome, expectation of yi, to avoid overfitting. Lastly, the regularized parameters are used to define an affine function using the negative binomial model to transform observed y into Pearson residuals. So I don't know how many of you have ever learned generalized linear models, because that's the topic we will talk very soon. Have you ever taken a class about generalized linear models? If so, could you let me know? Raise your hands. Yeah. So if you have the background, then how would you think about this paragraph? Is something you could directly understand if you just ignore the jargon here? How about Chen Xin? Generalized linear model. It's the negative binomial generalized linear model. So if we go just one more slide down here, this is a formula from the paper. So it's about the, and which we will introduce later, log link function. Yeah, so that's the mean part. But one thing which I found very interesting, I want to share with you, is a question I asked in the class this morning about what you see as a discrepancy or in the notation in this equation. Oh, but this is unrelated. The log 10 here is just a transformation. It's just, this is what you input as your predictor. You have only one predictor in the model. And this xi is your y, basically, your outcome. So that's not a discrepancy, because basically this is a log 10 transformation applied to something you want to input as a predictor, but you're not inputting it as the original scale. You input it after log 10 transformation. The right-hand side, this is the natural log. Yes. Yes. Yeah. I didn't get it. Could you say it again?
So, in a linear relationship, the predictor is y equal to x plus 3. I don't see that.
You don't see the linear relationship?
I would say linear X. It's already here, expectation of X.
Yes. It's already the expectation of X. And this is exactly what we will have in the generalized linear model. Basically, it's specifying the mean function about the expectation of the outcome, how it is related to the predictor or covariate. So that's not wrong, it's right. But we haven't talked about that yet. So it's actually a very preview of what we will talk very soon in a few lectures. But for those of you who are familiar or who have learned generalized linear model, I have a question for you. What is wrong with, or what is inconsistent in the notation here? Because I think as statistics graduate students or who would use statistics or write down equations, notation consistency is very important. Okay, I can give you the answer. Is that on the left-hand side, you have I. On the right-hand side, you don't have I. Yeah, whenever you have an index for I or J, you need to have it on both sides of your equation. If don't, then there's something missing. So in particular, this xi is variable I, so they're fitting a regression model for each variable I. Therefore, the model is specific for variable I. So basically, the model parameters, the slope, beta 1, and the intercept, beta 0, should carry index I. So to indicate a model specific for I. Okay, another thing which I found to be very relevant to say is this. So for equation, you have M, but down here you have MJ. So many people would thought, actually there was one student in my class who actually thought this M is a vector because he thought MJ is the jth element of M. However, here in this equation, everything is a scalar. There's no vector. So basically, what's happening here is that this MJ is like the jth observation. So the jth observation of the covariate, while xi should become xij. So basically, if you put mj here, it will become xij. So it's just that in this equation, we drop the index for observation, and we're just writing it in general. So to help you understand what I try to say here, let's move to the paper. So I will try to share the screen. So the recording is there. Yeah, I'll try to share the screen on my laptop to help you understand what I try to say. So basically, if we think about a simple linear model, we could write it for observation I, right? So basically, here you have y1 to yn. They are all real value down here. And I'm gonna make it bigger. They're all real value. And you have just one covariate. So therefore, it's just one feature, one covariate, one predictor, which we said in the first lecture. Then we write it x1 to xm. So the simple linear model, you could write it in the way as for observation I, then it's yi equals beta 0 plus beta 1 xi plus epsilon I. This is the one observation form. But what's in that paper, in that equation, it just didn't specify I. So in the unspecified way, it becomes y equals beta 0 plus beta 1x plus epsilon. So you see, I is dropped. But the confusion here is people might thought y as a vector. They might thought x as a vector. They might think y as a vector, x as a vector. The reason is that in our matrix form, if you remember, the confusion is if we write y as this, y1 to ym, x as this design matrix, 1, x, 1 to xm, right? Using this form, then in our previous lecture, we have this matrix form. Y equals x beta plus epsilon. But in this case, the beta is also a vector, including beta 0 and beta 1. And epsilon is a vector, has epsilon 1 to epsilon m. So that's why you see in these two forms, you both have y and x without the index, but you may confuse yourself. So that's why the suggestion is that if you're not writing the matrix form, if you're writing a model fund for one observation, try to keep the index. That's my suggestion. Otherwise, if it's not, you should define it very carefully. You should say, okay, this is the model for one observation, but I'm dropping observation index I for convenience. Okay, I have to say that this is something I hope we can do well in our paper writing, just to make sure that the notations are consistent. Otherwise, for experienced readers, they may guess what you mean, but you may lose some readers. Okay. All right, so that's just the opening of the class. I hope you find it relevant. And also, I noticed that another thing, people, especially in our department, master's students, MS students are required to write thesis. But I often notice that some of the LaTeX typesetting are not standard. For example, if you use LaTeX to write your thesis, you may not type log as, you may just type log instead of saying this \log, right? In LaTeX, this will be the one that give you the correct font for log, but this one will give you the italic thing because you put the log as in math font. So these are the small things I think quite important to make sure that your math writing is clear and easy to understand. Otherwise, using math is not really doing the job. It's not making things clearer, but more confusing. Okay, so let's continue with our lectures. So today we'll talk about lecture 3, ANOVA. So before we start, do you have any questions you want to ask? Or if you have taken an ANOVA class before, if you have anything you find confusing, you can let me know. And if not, then I'll just talk what I think is important. Okay, so last time we talked about, just as a very quick review, regarding the inference. Regarding the inference of this coefficient vector beta, right? We give some cases about whether it's one component, say beta j. If on the test whether this beta j is 0 or not, we talk about the t-test. T-statistics and t-test. And if we're talking about some subvector, we call it, say, beta 2, that's RP2 dimensional. So P2 with P2 greater than 1, right? More than 1 dimensions. Then we talk about the wall test. And then we give you a more general way to do the test, which is the likelihood ratio test. And in the likelihood ratio test, we are comparing H0, which is a constraint model. And maybe we can just say loosely as a smaller model where you have fewer parameters to estimate versus H1, which is the full model. And in the likelihood ratio test, we will look at negative log of like -2. The test statistic is -2 times the log of the likelihood ratio. Okay, and the likelihood ratio is the maximum likelihood under the null versus the maximum likelihood under the alternative, which is unconstrained. And in the linear model case where you have the epsilon following Gaussian, multivariate Gaussian. So basically it's n-dimensional Gaussian, but each epsilon I is independent of the rest. So this Gaussian will have a diagonal n by n covariance matrix. So basically, I'll just write it here. So under this assumption that this follows an n-dimensional Gaussian with the mean 0 and the covariance matrix at sigma squared times the n-dimensional identity matrix, under this assumption, then we can easily write down the likelihood based on the Gaussian density, and then we can get a form as this. The residual sum of squares under the null minus the residual sum of squares under the full model unconstrained, but we would need sigma squared in the denominator, which is unknown. So then the question we discussed last time is how do we estimate the sigma squared? We could use the residuals from the null model, smaller model, or from the full model. Then which one should we use? And we said that we actually use the full model. And this is under the assumption that the full model is the correctly specified model. So under that, we want to see whether the smaller model is satisfactory because it's simpler. Okay, and also this is related to the asymptotic distribution. So when we plug this in, right? So basically to plug in, what we are using actually is the residual sum of squares from the null model, which is bigger because under the null model, the fitting must be less well, as we are just using a less complicated model to fit the data. So the residuals are bigger. And this is just the sum of squared residuals. So that's why this is bigger than this one. So we have a non-negative part for the numerator. And for the denominator, we just use RSS from the full model, assuming that the model has P parameters. I mean, by P parameters, we mean the beta is P dimensional. We have one intercept, P minus 1 slopes. So then this is the degrees of freedom, n minus P. So that's how we estimate the sigma squared. That's where we end last time. And we said that the asymptotic distribution for this one, it will follow asymptotically under H0 to this chi-square distribution, where the degrees of freedom is the difference in the number of parameters between the smaller model and full model. So if we say we're doing this sub-vector testing and they differ by P2 parameter difference, then this chi-square would be P2, will have P2 degrees of freedom. So that's the result. And this result was very useful in the old days because people can make up a table for chi-square distribution for each degree of freedom. And we just look up the table and find the corresponding probability tail probability for this test statistic. And that will give us a p-value. Okay, do we have any questions about this? In particular, I kind of skipped the p-value calculation because I think that's a basic thing and people should be aware. All right, so for this one, we are treating the right tail probability as the p-value to reject the null hypothesis that we have a smaller model. Okay, so basically that's what we did. Then if we want to follow up to talk about ANOVA, which is itself a commonly used jargon in statistics. ANOVA, how many of you know the full name of ANOVA? What does it stand for? I think the full name is actually more informative than the short name. V stands for variance, correct. So it's analysis of variance. That's it. Yeah, I think the full name is actually more informative. So what it tries to mean, what it means is that we would try to decompose the variance of our outcome. I'll just call it YI. So I'm talking about the ith observation outcome. The variance of yi, we try to decompose it into two parts. So the variance explained by model. Okay, so in this case, it's the variance explained by xi transpose beta. In particular, we don't know beta. So what we're trying to use is this beta hat, because that's how we estimate it as our model, plus the unexplained variance, which our model cannot explain. And this is based on the residual. So it's this EI. Yeah, please be clear that it's EI, not epsilon I, because epsilon I is the error term, which we don't observe. What we only have is xi as the covariate vector with p-1 covariates and the yi. That's our data. So we have to infer beta hat by some optimization. Like V square is one way to do the optimization. And then with this called the predicted or fitted value, then we have the residual. So again, just a reminder, yi hat is just xi transpose beta hat. That's our fitted value for yi or predicted value. And then ei is just yi minus yi hat. And the introduction of the hat matrix is based on this, right? So the hat matrix is just in the matrix form. So this y hat as an n-dimensional vector can be written as x times x transpose x inverse x transpose y, because this is how we estimate the beta hat. And the hat matrix is for the whole thing before y. Okay. So now we're going to introduce a very important property about this ANOVA. And this is a key starting point. That is the y vector, y1 to ym, and the y bar vector, they share the same average. So this is a very important fact to know. That is, if we take the summation of yi's, I from 1 to m, this is equal to the summation of yi hats, I from 1 to n. So even though one is the observed outcome values, the other is the predicted or fitted outcome values, but they share the same sum and therefore the same mean, same average. And why is that? And the derivation, again, can be made much simpler with the matrix form. So the idea is that this is equal to the inner product between a vector of ones. So one with n-dimensional vector with all the ones times transpose times this y bar. This is the definition by inner product as the sum, right? And then what we can do is to make it here. So basically, what we try to say is that if you put this everything basically have, and what you would have is what? Now let's look at the design matrix. That's the thing. In the design matrix, if we scroll up here, the first column is ones. So basically design matrix can be put as a vector of one and your covariates, right? And also your basically your x, let me just put it as your covariates. Just put it here, yeah. So therefore, you can see what happens is that if I take the x transpose, of my design matrix, then the first row would be this, would be a row of ones. Then it's the covariates, all the covariates matrix, I take the transpose. So I can ignore them. But basically, what I need for here is just the first row of my X transpose. And what happens here is that if I take the X transpose Y hat, the magic will happen with this hat matrix. I put this inside, then I put this down here, then it's X transpose times X, X transpose X inverse X transpose Y. So you see that I can have this nice cancellation in the matrix form. So I'm just having X transpose Y. Then you see on the right-hand side, I also have the X transpose, same as the X transpose here, and both have the first row as a row of ones. So that's why this will tell me that if I look at the first row only, then it's 1 transpose Y hat equals 1 transpose Y. So that would directly give me the result. And this is because of the fact that the design matrix first column is a column ones. That's the reason. So it's a direct result of this. So with this result, you can directly have this yi square, yi sum equals to yi hat sum. I hope this makes sense. Okay. Any questions? All right. If not, then an implication of this becomes this very useful formula, and this is the core of ANOVA. That is, if I take the summation I from 1 to n, yi minus y, I call it y bar square. Some people may refer to this as the ym bar. So it's just whether you denote the sample size here or not. This ym bar is defined as just the average of yi, which based on our previous argument, let me try to make it clear. Which based on our previous argument is the average of yi bar, y hat. Okay, and this term, we can decompose it. Basically, we can introduce yi hat and then remove it, right? So we can use this very common trick by doing yi minus yi hat plus yi hat minus y bar n squared, okay? And then we can open it up. We will take this as one term. We will take this as another term, just like the square of a plus b. Then we know when we open it, it becomes a squared plus b squared plus 2 times ab, right? So we will have the same expansion here. And then you will actually have it as, let me just write one more step, yi minus yi hat squared plus yi hat minus ym bar squared, and the cross term 2 times yi minus yi times yi hat minus ym. Okay, so that's the cross term. But the first two terms are the key things to keep in mind. What we want to show here is that the sum of the cross term would actually be equal to 0. Okay, and for this one, I will leave this to you as an exercise for you to verify why this is equal to 0. So it's yi minus yi hat times yi hat minus ym bar. Okay, but and you may make use of the matrix form again, like the inner product. It can be considered as the inner product between the residual vector e and this is y bar, but they say y hat for the fitted value vector minus ym bar times 1. So you can verify this sum is 0. But we can show that with that being 0, then we can open it as summation of yi minus yi hat squared plus summation yi hat minus ym bar squared. Okay, so this is the key thing. So this term is decomposed into these two terms. And we give it a name to each term in the ANOVA. So we call the left-hand side, this term, we give it a name. We call it sum of square total. Sum of squares total. And we call this term as the sum of squares error. And like we said last time, this term can also be called as RSS, which we just used is the residual square sum. So they're all about the part we cannot predict well. And this one is called the sum of squares regression, short as SSR. So the short way to memorize this or to write it is SST equals SSE plus SSR. And the SSR is the part your model can explain. SSE is the part your model cannot explain. And SST is the total variance you observe in your outcome, your one. Okay. And in some specific applications, people may use different words, different terms to describe this decomposition. So it's basically a variance decomposition. That's the core of ANOVA. And in statistics, I think there are a lot of important implications of decomposing the variance. For example, if we believe our model has some scientific meaning, then we may think this is the part our science can explain, and this is the part we cannot explain, and this is our data. So we may think, okay, the science part, the regression or model part is what we think as the meaningful signal, while the error part, residual part, is what we see as what we cannot handle. It's kind of due to the noise in our data, technical variation, and this is the total variation. So therefore, I would say this is a very fundamental way to think about our data. How do we look at the uncertainty in our data? Why are the N observations different in Y? How much of that can be explained by covariance? How much of that are something we cannot handle? So in statistical genetics, people actually look at Y or the outcome as a trait. So, the problem genetics want to study is how much can the variations in our DNA explain the trait, the different trait we have. For example, why do we have different heights? Why do we have different blood pressure? Each one is considered a trait. And we want to use our genetics to explain it in the hope that, okay, if the genetics can explain it, maybe we can identify which part of our DNA is contributing to this trait. And if this trait is a disease, hopefully we can somehow modify our DNA to cure the disease. That's the ultimate goal. But the logic is that we hope the genetics is the model to explain more about the trait variance. And in genetics, this ratio, actually, in statistics, we call R squared. It's SSR over SST, okay? So basically, it's about the proportion of the total variation that can be explained by your model. In genetics, it may be called heritability. It is a jargon, but this jargon means that how much of the trait is heritable, and that's explained by the model. Okay, so linear model is still very widely used for explaining our data, especially if we want to understand the variability. And what you can change is the model complexity. So as we know that by adding more and more parameters to your model, you can make yi hat closer to yi for each observation. But we have worry about that. This is overfitting. By overfitting, we mean that your SSR is capturing the noise part of your observation of your yi. So therefore, that model may not be so meaningful. And if we believe that the technical variation or the error term are independent from data set to data set, then this complicated model will not fit well to the new data set because a new data set has independent noise. And that's why we would see, oh, the prediction error is small in the data we fit the model, the training data, but it's large on an independent data set. And that's what people call overfitting. So overfitting is because you think the model captures the noise part of your data, not just the signal. Okay, so let's see what we have at the two extremes. So I think before we introduce the ANOVA table, which I think will be simple after we have all this, but I think it's good to consider the two extremes of our model. So two extremes on both ends of our linear model. So because in our linear model, let me just remind you again, I'm writing this model for one observation. For linear model is xi transpose beta plus epsilon I. So note that my xi includes the intercept. So the first element is 1. Okay, on the one extreme, on the simple side, we don't want to include any covariates at all. By not including any covariates, how would you predict yi for each observation? Because I don't want to use my xi at all. I don't want to use, for example, if I want to predict a person's height as the trait, I don't want to use this person's any characteristics. I just want to predict. No information about this individual. Yes, the average, right? We'll just use the population average height. Yeah, that's the simple model. And this is called intercept only model. So you just have one intercept. So in this case, I would just write it as yi equals beta 0 plus epsilon I. So the differences in yi is purely due to the error term. The intercept is the same. And like back to what I said in the beginning of the class, you can see I'm still obeying this principle that if I have I have it on both sides, right? It's on both the yi, in both yi and epsilon I. If I write yi equals beta 0 plus epsilon, that will be problematic. Where does I go? Okay. On the other extreme is the complex side. How many parameters can I afford at maximum? Yeah, number of your observations. You could have a separate mean for each yi. So in this case, we will just write yi as equal to mu I plus epsilon I. So each yi has its own mean mu I, and these means can be totally unrelated to each other. So we call this, so the top one is intercept only model. The bottom one is called saturated model. Because when you use this model, you can already get perfect prediction, right, for each yi. You just predict, so in this case, you just set ui hat, your estimate to yi. Then you get perfect prediction. Okay, so what ANOVA does is trying to compare linear model with the intercept only model. And this is called the null model. So what ANOVA does is still a model comparison, just as what we did in the likelihood ratio test, in the wall test, the t-test is all about model comparison. But ANOVA is trying to compare linear model with intercept only model. And this intercept only model is treated as the null model. All right. So a typical ANOVA nowadays we don't need the table that much as before, because in the old days, before we have computers, we actually use the table to do hand computation. We do the calculation on paper. But now we don't need it, right? We have the computer to help us. But it's good to know the thought process. How do we think about the decomposition? So we already have this. So we would have the sources of variation as the regression model part, residual part, and the total. So basically, in this case, the first row is just the SSR, the variation explained by model. Second row is SSE, and we know that they add up to SST. Okay. That's what we have after the decomposition. But to really compare the model to the linear model, which give us SSR, to the null model, we need to how to say that, standardize the terms. Because I think your intuition would be, if the model is better than the null model, then I expect this SSR to be big than SSE, right? Their relative magnitude. Because if this is big, I think the model is informative, it's doing well. If this is big, SSE is big, I think the model doesn't fit well. So that's the intuition. But to compare these two quantities, we actually need to standardize the SSR and SSE because they have different degrees of freedom. And that's the key thing. The degrees of freedom as a column would be something we need to use to standardize each. Because otherwise, if we have a very, very complex model, as I said, like the saturated model, SSR can be huge. It can be equal to SST when you have a saturated model, right? The model just explains everything. So the degrees of freedom is actually P minus 1. And for SSE, it's M minus P. And for total, M minus 1. Okay. Yes, for each observation. Yeah, there's no information borrowing. There's no information borrowing across observations, right? For each observation, we just give its own parameter as its mean. Yeah. It's not a useful model at all, but we data. Yes, describing data. It's just like if you didn't take any statistics classes, I give you a scatter plot of y1 to yn, x1 to xn, one-dimensional covariance. How would you fit a curve? You may just draw curves to link data points together, right? That's what's the, yeah. Okay, so how do we interpret the degrees of freedom? I think this is the most challenging part. So for the SST, if we scroll up to here, to the formula of SST, we only add one constraint, which is the average. The average is the only constraint to tie the endpoints together. So we lose 1 degree of freedom. And in the SSE, the residual, we already see this, right? When we use the residuals to derive an unbiased estimator for sigma square, if you recall, the degrees of freedom is n minus p, because we have p parameters in the model that takes away the degrees of freedom from the residual. And if we want to add up these 2 degrees of freedom to n minus 1, then we have SSR. So how do we interpret this SSR, the model degrees of freedom? Why is it p minus 1 instead of p? Because the model has p parameters. The reason is we are thinking about the model's gain over this SST, the intercept-only model. So compared to the intercept-only model, this model only has p minus 1 additional degrees of freedom. And also you can see that this is related to the fact I just described, that y1 to yn has the same average as y1 hat to yn hat. So they share the same mean. Even though for the linear model, we achieve this same mean property as the intercept-only model, because in the intercept-only model, if you just use the beta 0 hat to predict each yi,
then you will still get the same yn bar as your estimates for the y. So you will achieve the same equal average between the fitted values and the original observed values. But what you get in this model, in addition to this baseline, this null intercept only model is p-1 degrees of freedom. You add more to that. We have more freedom than that, I should say that. Okay, so then using this, we just do standardization. We divide each sum of square by its corresponding degrees of freedom. And we call the top one as MSR. It's mean squared regression. So this is sum square regression. Mean square regression is defined as SSR over p-1. You divide the SS by the degrees of freedom. And for this is MSE, mean squared error, right? Now you see where this name comes from. We still use the mean square error as the common criterion for evaluating prediction models in supervised learning for prediction problems. This is SSE over M minus P. Finally, down here, we don't care about this because we would not use this anymore. The test statistic we will use will be based on MSR and MSE. And this is called the F statistic in ANOVA. The F statistic is defined as MSR over MSE. Okay. And because it's sum of squares, and we told you the intuition that sum of squares typically follows chi-square distribution. If we can write it as the sum of some squares of independent standard normal random variables, right? We know if we have two standard normal variables, standard normal random variable square, add up, if they are independent, then the sum is chi-square 2. If we have three of them, chi-square 3, etc. So it depends on how many independent standard normal variable squares we can decompose into. And that's related to the degrees of freedom, actually. So therefore, we have to talk about this F distribution as the ratio of two chi-square random variables, independent, and each divided by its degrees of freedom. So based on all these arguments, so this ratio called F statistics would follow an F distribution with numerator degrees of freedom p-1, denominator degrees of freedom m-p. And this is under the null distribution, null hypothesis. And under the null hypothesis, what is that? It's basically the linear model is not doing better than the intercept only model. So here the null is the intercept only model. So you can see this as how to say it, a third way for testing model comparison. The first way is the wall test. Second way, and t-test is a one-dimensional version of the wall test. Second version, likelihood ratio test. Now we have ANOVA. And this ANOVA compares linear model to the intercept only null model. Okay. Does it make sense to you? Okay. Then next topic we move on to is hierarchical ANOVA. Hierarchical ANOVA. So what this does is that, okay, now we are not comparing a linear model to an intercept only model, but we are comparing a linear model with more covariates to a linear model with fewer covariates. Okay, so that's what we do. Basically, we can compare. So if I use the R command to write it, is yeah. Yeah. It means that the data are from the intercept only model. Yeah, the intercept only, which means that in the linear model, except the intercept, all the slopes are 0. That's the null hypothesis. Sorry?
We are assuming the data is generated from intercept only.
Yeah, data is generated from intercept only model. Yeah. Yeah. So that's why I've said it's the same problem you can tackle with the wall test or the likelihood ratio test. Yeah. And also, a lot of the differences is between whether you go more asymptotic by changing the F distribution into a chi-square distribution. I think that's something we talked about earlier in the class. We said there's some correspondence between T distribution and normal distribution, and between F distribution and the chi-square distribution. So one is even more asymptotic if we use the normal or the chi-square. But T distribution and F distribution are less asymptotic, but you need to have the normality assumption of your error term reasonable. Yeah. Okay, so for hierarchical ANOVA, we are again comparing two models. One is a smaller model which have fewer covariates. So maybe I'll just write as Y regress on X1. So X1 could be more than one covariance, but I'm just putting it into X1 as a chunk, a block of covariance. And we have a bigger model, larger model. And that's Y regress on X1 plus X2. So X2 are some additional covariates you want to consider. And in this case, you are just trying to answer the question about whether I should move from a smaller model to a larger model, which basically means that whether adding additional covariates X2 give you a better model for explaining your data. Again, our attitude is always that adding more covariates is not necessarily better. Adding more parameters is not necessarily better because we might be fitting noise in our data. And again, as I said in the first lecture, nowadays we should think about how do we embrace the AI algorithms, which are on a very different end of the spectrum. We are not afraid of over-parameterization. We are not afraid of adding a lot of parameters to our model, having a large model. But what is the position of small models? Do we still need small models for what, right? Or do we need large models for what? I think this is the question we should think about, especially if you consider yourself to be statistician or trained with statistics, and you will face questions from the public like this one. Well, how would you answer the questions? And are the things we learn in this class still valuable in what way? So I would say, maybe this is something I cannot give you a very good answer myself because a lot of things I think in my mind are still scattered. But I think this ANOVA kind of thinking, how do we look at the variance in our data is always there. It's fundamental, right? Because if you are not afraid of having a saturated model, given here, saturated model, what does it mean? It means that you are basically assuming your data to have no noise, right? If there's no noise, then just fit it. Just try to predict as well as possible. It doesn't matter. But if the data's noise is not negligible, this is important, right? You don't want to have something that will not work on another data set because another data set have different noise distribution. Okay, I think I want to hear your thoughts on this, especially during your final presentation, something you can make outside of this class to make your points valuable outside of our community. Why do we need different models? And especially, you know, as a user, not a method developer, you might just prefer to have one method that always works, right, for your problems. But we know it's not possible, right? Then how can we help? All right, so yeah, I think this question to keep in mind. Anyway, so hierarchical ANOVA is trying to compare these two models, but one thing, x1 only, I may just write it as x1, maybe I'll just keep the slope, yeah. I keep the slope and I write x1i for my ith observation, transpose beta 1 vector, because this xi may be multidimensional, plus epsilon I. Okay. That's one model, the smaller one. For the bigger one, yi, okay, I'll just use a different set of parameters. Beta 0 tilde, x1 I had transpose beta 1 tilde plus x2 I transpose beta 2 tilde plus epsilon I tilde. This is the larger model. So the reason I try to add tildes to my second model is that I want to let you know that the two intercepts are not the same parameter, and the two slopes for x1 are not the same parameter. Because once you have a different model assumption, then the effect of the covariates in x1 are no longer the same. Okay, you should be aware of this. Especially, the covariance in x2 may be correlated with the covariance in x1. So when this happens, you will see that when you fit this larger model versus when you fit a smaller model, the beta 1 coefficients you get will be different. Okay. So how do we interpret this? That's the thing. So hierarchical ANOVA is basically helping us decide whether this beta 2 tilde is 0 or not. So that's the problem wall test is trying to solve as well, or likelihood ratio test. Okay, so in this case, we would do this. So we would call the variance explained by the first model. By the first model with x1 as the covariance only, we call that SSR sub 1 for the x1's explanation. And we call this SSR 1, 2, means that we include both x1 and x2. Okay. All right. So in the hierarchical ANOVA, besides this SSE, the residual part, we will have two rows. Sorry, we should have with two rows, not just one row. Here we have just one model, but in hierarchical ANOVA, we have two rows. One for the smaller model, one for the larger model, one for the residual. And the residual, the errors, the sum of square errors will be from the larger model. All right. So basically, in the ANOVA, we would have these. We call this first column sources of variation. Okay. The first model we consider is x1 only. Second model, we have x1 and we give it x2 as an addition. So given x1, we add x2. And then we have the residuals. And then last line, total. Okay. Then the second row is the sum of squares. So it's about how much can we explain by each. So this is SSR1. And this is SSR2 given 1. And it's defined as the difference between the two. It's defined as SSR1, 2 minus SSR1. The reason is we know by adding additional covariates, we could explain better. We could explain more of the variance. So SSR1, 2 is for sure no smaller than SSR1. Okay, so we take this non-negative difference as SSR2 given 1. And the residual is SSE1, 2. It's from fitting a full model. Okay, and here SST. So you see in hierarchical ANOVA, when we do the decomposition, we're decomposing SST into three terms: SSR1, SSR2 given 1, and SSE1, 2. And degrees of freedom. We start from the simple ones. For SST, it's n-1. For SSR1, 2, maybe I should give you some ideas here. So basically, we would say this small model has P1 parameters, P1 coefficients. And for this larger model, let's say we have P coefficients, okay? So P greater than P1. That's the setup. Then the residuals is from fitting the full model, right? And that will give us M minus P degrees of freedom. Okay. And then we should go on. So these two will together have P minus 1 degrees of freedom, but we would have X1, which is this model, smaller model only. It has P1 minus 1 degrees of freedom. Okay, then this second model, the additional degree of freedom we get is by adding the X2 covariates, and that's P minus P1 degrees of freedom. So we can also decompose the degrees of freedom in this way. All right, and then when we look at the F statistic, what is that? We're trying to see whether this contribution, X2 given X1, is significant. So to answer this question, essentially, we are going to compare this SSR2 given 1 to the errors, to the SSE12. So we'll compare these two. So basically, for the MS, mean square column, we care about these two rows. So we will define MSR 2 given 1 just as SSR 2 given 1 divided by this P minus P1, divided by the degree of freedom. And MSE 12 is just SSE 12 divided by M minus P. So it's about our estimate of the error terms, the sigma square. And then F statistic is defined as MSR 2 given 1 over MSE 12. And the F distribution, for the null distribution, the degrees of freedom will be P minus P1 and N minus P corresponding. Okay, so that's exactly what we did for the hierarchical. So you can see that if we want to do it in another way, that is by swapping X1 and X2. We can start with X2 as the smaller model, and then we add in X1 to see whether the X1 has significant contribution given X2. But then we'll get a different hierarchical ANOVA table and different conclusion because we're talking about different questions. So therefore, for hierarchical ANOVA, the key is to know the order you want to test your covariates for. So typically, the smaller model is a baseline model people have some good faith with. And then you want to see, okay, now I have collected additional variables as possibly useful covariates. Should I add them to my model to see if my model can explain better? Then that will be your X2. Okay, so still having the question to ask in your mind is the most important thing before you do the modeling. And then you can see this is the practical part of statistics. It's not just math, but you have to formulate the problem and you have to know the question. Okay, do you have any questions? Yes.
Examine the X2 adding additional values.
Exactly.
So does it not compare X2 given X1 with X1 instead of the regular?
I'm sorry, what should we compare what?
Again, when you get to the X, right?
Yeah.
So do not compare X2 given X1 with the MS of X1
And oh, all right. Okay, the reason we don't do that is because the additional contribution made by X2 given X1 may not be bigger than the contribution of X1, but it's still something, right? So therefore, when we say significant or not, we are comparing this additional contribution to the contribution of residuals, because the residuals contribution is what considered to be the noise, the technical variation. So when we say this contribution of X2 given X1 is significant, we mean it's more than the noise contribution. That's the rationale. It's not compared with the X1's contribution. Does it make sense? Yeah, X1 could still be the dominant effect. That's okay. But yeah, but given the dominant effect, we still have some additional gain, right? So therefore, you can consider the residual SSE as the baseline contribution you are comparing against. Whether you are doing it better than that, you consider to be significant. Yeah. And then another question. Yeah, I'm just saying that here you need to first know what is your baseline model, which is X1 only. And then you are evaluating the additional contribution of X given X1. Because you could do it the other way, right? Given my X2 as the baseline model, is there additional contribution of X1 given X2? But you will get a different answer because it's a different question. Yeah, that's what I mean. Okay. All right. Okay, let me see what I want to cover else. Okay, and I think it's something I want to add just as a side note. Okay, after the hierarchical ANOVA. The side note, which I want everyone to be aware, is this. Of course, yeah. Can I evaluate what? Can I evaluate interaction? Of course. Yeah, because typically we don't include interactions in our linear model, right? We start with an additive model. But if you want to add, okay, let me try to say this as that's a very good question. Yeah. So the question is interaction terms. So let's look at this scenario. We have two covariates, X1 and X2. So therefore, our data points would be like X1I, X2I, YI. Okay, that's what the data points are look like. So in this case, we could have two models. One is called the additive model, in which we assume the effects of the two covariates are just additive. So in this case, the model will be written as yi equals beta 0 plus beta 1 x1i plus beta 2 x2i plus epsilon I. That's the additive model. And we could have the interaction model. So we add the interaction term between x1 and x2. Then the model will become yi equals beta 0. I call tilde because they're no longer the same parameters. Beta 1 hat tilde x1i plus beta 2 tilde x2i plus beta 1 2 tilde x1i times x2i plus epsilon I. So then in the hierarchical ANOVA setting, this is the additional covariate you would add. So then this is your baseline model. This is the larger model. Then you would do the same argument as we did in the hierarchical ANOVA. So you will basically consider this to be your X2 and these two to be your X1. That's it. Yeah. So that's exactly right. So you're treating this as an additional covariate. So basically, when you fit this model in your programming, what you would do is that for this one, your design matrix would just be a column of ones and x11 to x1n, x21 to x2n. So it's a 3-column design matrix. Now for this one, the design matrix will get an additional column. You still have a column of ones, x11 to x1n, x21 to x2n, and you have additional column as x11 times x21, x1n times x2n. That's it. So that's how you are going to do it. So actually, this class in the homework problems, I'll try to let you do some of the manual programming to help you understand what's inside the R package. Because if you just use the R function, the LM function for linear regression, you can automatically get the result, right, for the two models. But if you can do this manual coding and do the X transpose X inverse X transpose Y, you can check it yourself to see how the results are like. All right. For the last few minutes for today, I think I want to talk about this interesting asymmetry of simple linear regression. So basically, if we talk about this simple linear regression scenario, one covariate, we just have the pairs xi, yi. Then when we want to fit a linear line between the two variables, we can do it two ways. So what I mean is that you could write model as yi equals beta 0 plus beta xi plus epsilon I, or beta 1 xi. Yeah, this is you regress y on x. Or the other way around is you could treat xi as your outcome. I call it alpha 0 plus alpha 1 yi plus eta I. Try to use a different notation. So between the two models, you consider x or y as the outcome. So the outcome formulation is different, right? So because in many cases, if you don't have a clear mind about which variable is better, can be better used as the outcome, the other as the predictor covariate, you may run into this problem. Then what I try to say here is that we have a very interesting asymmetry in the two ways. So I'll just give you the formula for the, how to say that, for the slope estimate. So if we do the least square to fit the two models, then we know that beta 1 hat in the scalar form, not the matrix form, can be written as this. It's the Pearson correlation between the two vectors x and y. So I'll just say x is x1 to xn, y is y1 to yn, the two vectors. Then beta 1 hat has the form Pearson correlation x and y times the standard deviation of y divided by standard deviation of x. That's a formula we learned about simple linear regression. And you can show that it's the same formula as the matrix form, x transpose x, inverse x transpose y, same thing. And the alpha 1 hat for this second linear regression is equal to still the Pearson correlation between x and y, but as we put x as the outcome, it's SD, standard deviation of x, divided by standard deviation of y. So what you can get out of it is that even though you know that, okay, this is the effect of x on y, this is the effect of y on x, but they are not, beta 1 and alpha 1 are not the inverse of each other. That's the key. Because if you look at here, you can clearly see that if I take the inverse, yes, I can change the SDY and SDX, but the Pearson correlation is still there. So basically, what I want to say here is beta 1 hat is not equal to 1 over alpha 1 hat. That's the thing. It's a very interesting result from the least square. And the reason is that in the least square, when we minimize to do the optimization, we're minimizing the residuals of the outcome variable to the fitted line. It's not symmetric between the outcome variable and the covariate. That's the reason. If you want to have some regression lines that satisfy this inverse relationship, there's another type of regression, which we'll not introduce here, but it's called the major axis regression, just for information if you're interested. So the major axis regression, when we fit the line, we treat x and y symmetrically. We're not just minimizing the vertical residuals. That's the key difference. Yeah, people may minimize what's that? You may minimize the vertical, right? The vertical distance, not vertical, it's called how to say that, orthogonal, or it's perpendicular distance between the point to the line instead of the vertical distance, as in this way. Yeah. And just for another information, if you are minimizing the perpendicular distance, basically, in this case, the line you get is the first principal component because of that. Yeah. So these things are kind of connected. Yeah. So it really depends on whether you have the formulation about knowing which is the outcome. I think that's the key. All right. So we will stop here for today. And on Wednesday, we will meet at our regular time at 12:30 in the Royce Hall. Okay, I'll see you then. Bye everyone on Zoom.